So the next session is about symbolic execution and constraint solving, right? And the first presentation will be given by Paizhen Yao. The title of the paper is fast bit vector sets, right? And so Paizhen, it's all yours. Sure.
Okay. Thank you for coming to this presentation. I'm Paizhen Yao from the Hong Kong University of Science and Technology. Today, I'm happy to share our recent work about speeding up SMT solving. The problem of SMT solving is to decide if a given formula is satisfiable in some background theory. For instance, let's consider this a simple equation or a simple formula. If x is a real number, then we say it's satisfiable, meaning it has a solution. However, if x is an integer, then this formula is unsatisfiable. Over the past 1 or 2 decades, SMT solvers have had a very high impact on SE and PR research, with many practical applications, such as testing, verification, repair, and synthesis. Over the past years, many theories have been introduced, like integer, real, bit vector, string, and ADT. The theory of bit vector is of crucial importance for software analysis. In short, a bit vector is a fixed size integer, like a 32-bit integer or 64-bit integer. Bit vector is important because it can model the machine arithmetic faithfully and precisely, such as nonlinear computation, overflow, underflow, and bitwise operation. If a tool models a 32-bit integer as an unbounded integer, then the tool might be unsound. Our work will focus on speeding up bit vector constraint solving. In theory, it has a very high time complexity, and in practice, it has been reported by many different teams over the years that the overhead of assembly solving can be the performance bottleneck of the tools. It can even take more than 90% of the total time. Therefore, speeding up assembly solving is always in urgent need. The dominant approach to solving bit vector formulas is called the eagle approach. The eagle approach has 3 major steps or 3 phases. In the first phase, it will apply some lightweight rewritings of simplifications, as shown in the examples below. In the second phase, which is the crucial phase, it will translate the bit vector formula to an EQ satisfiable Boolean formula. The idea is to encode an n-bit integer with n fresh Boolean variables, as shown in the following example. If we know the value of b1 and b0, then we can calculate the value of x. Also, to encode the bit vector operations like add and multiply, it will use something like hardware circuits. Let's consider a simple expression, x bitwise y. The idea is to first introduce 2 fresh variables, d1 and d0, to represent the calculation result of this expression. And then it will add the Boolean formula to encode the semantic of the operation. This procedure is very similar to a compare. We compare an integer program into a binary program. Finally, in the last step, is we usually call an off-the-shelf SAD solver. To the best of our knowledge, over the past years, most optimizations for eager bit-to-bit solving focus on either the first phase or the second phase. Their goal is to reduce the size and the complexity of the Boolean formula. However, if the size of the Boolean formula cannot be reduced, the final phase would be very expensive. A recent work also claims that the SAD solving phase is often the performance bottleneck of modern bit-to-bit solvers. Our work will focus on speeding up the third phase, SAD solving. I will first give some background about the SAD solving. Essentially, the SAD solver has two searches through an exponentially larger search space. In modern SAD solvers, at each iteration, there are two major steps. First, the solver will select a Boolean variable and give it a value, which can be 0 or 1. After assigning the value, it will deduce or infer the values of other Booleans from the current assignment. Let's consider here a very simple Boolean formula. It has two clauses and two variables, A and B. Suppose we first choose variable A and give it a value 1. Then the SAD solver will deduce that B should also be 1. Because otherwise, the second clause would be false. Now we have successfully solved this formula. It is satisfiable. However, if we first choose variable B and give it a value 0, then the solver will deduce that A should also be 0. Because otherwise, the second clause would be falsified. Now, in the current assignment, B equal to 0 and A equal to 0, the first clause would be falsified. Here, the solver has to perform some backtracking and starts another round of search. As we can see, the order in which we select Boolean variables and the value we give it to him can affect the search procedure, and is crucial for the performance of SAD solving. Based on the ideas, there's a lot of work in the past decades. Most of them are proposed for purely SAD formulas, like those from hardware model tracking. They only contain Boolean variables. However, there's little knowledge on improving SAD solving algorithm in the context of eager bit-to-bit solving. So in this work, our work slogan is to break the conventional ladder design by infer and preserve word level information to guide the final SAD solving stage. Specifically, we propose to utilize two word level analysis, interval and dependency analysis. First, as we have introduced, we can calculate the value of a bit-to-bit if we know the value of their corresponding Boolean variables. So if we know the interval of a bit-to-bit, then we can partially fix the value of their corresponding Booleans. Also, in real-world programs, many variables may involve in simple computation, like a simple local assignment and a simple even linear branch compilation, which means we are able to process interval information for some variables. Now let's consider a simple example. Let's assume X is 8-bit and send integer. we will use 8 booleans to encode X. Also, the formula will be translated to a Boolean formula. Let's assume all the red points are the feasible solution of the formula. If we are able to infer that X is less than 4, then we can soundly deduce that B7 to B2 must all be 0, because otherwise the value of X would be larger or equal than 4, at least larger or equal than 4. Okay. Our second idea is to leverage the dependence between program expressions. In real-world software, it is often the case that the variables and the expressions have some dependence relations. For instance, the expression X bitwise Y are dependent on X and Y. So our goal is to prioritize the order of selecting Boolean variables for assignment. In the former case, in the former example, we will give higher priorities for B and C than D. Internally, if the value of B and C are given, then the value of D would be deduced automatically. Here is our high-level idea. If you are interested in the details, we can discuss personally or by email. We have implemented the techniques on top of this assembly solver. We will also compare with it with 2 existing solvers. Specifically, CVC4 has a state-of-the-art lazy solver, and Bullicta is the champion of the assembly competition in the bit-weight track. We apply our solver to 3 symbolic analysis platforms, which analyze 30 real-world subjects. The size of the programs range from a few thousand to about 4 million lines of code. Anger and QSIM are 2 symbolic executors for binary code, and Pinpoint is a static bug finder for C or Java programs. In total, we collect about 7 million assembly queries. Also, we observe that some symbolic tools like Pinpoint or Clee have their own simplifications and caching, which means they can prolong some simple queries. Therefore, we only dump a query when it is sent to the when it is sent to the backend solver. For the first comparison, we compare with the optimized D3. On average, our approach can improve the performance of D3 by 3 to 6 times, and it can solve more queries on all the 3 groups. Compared with CVC4 and Bullicta, our solver is about 7 and 2 times faster. Also, it can solve much more queries than CVC4. In addition to running, finally, we also apply our solver to the 3 tools and see if it can improve the performance of the client analysis. Both QSIM, Anger, and Pinpoint use D3 as their default solver, so they can benefit from our solver directly. In summary, our tool can improve the performance of Anger and QSIM by about 1.9 and 1.6 times. Here I show a case study where we use Pinpoint to detect the non-pointer bugs in 3 large-scale programs. Okay. We have to argue that such a speedup is non-trivial for a static bug finder. For instance, let's consider Google V8. Previously, pinpoint takes about 12 hours. Now, with our solver, pinpoint can finish in about 5 hours. It's enough to make an impractical tool be impractical. For instance, this means pinpoint can analyze V8 in neatly build. As a future work, first, we believe that the water level information or programming information can be leveraged to improve other components of SAT solving. We are not exploring in those directions, but I believe it's promising. Also, second, currently we do not support array theory. We only support the bit-weight formulas. But array theory is important for many symbolic executors like CLI, BAP. Depends on their memory model, which is also the topic of the next presentation. Thank you.
So thank you, Paizen. So far we did not receive any questions on the Slack channel, but I have a couple for you, right? And at least, I mean, this can give some time for people to think about the questions. But one question that I had was about the benchmarks that you've used. I mean, it wasn't clear whether these benchmarks came from well, symbolic execution, for example, of these programs, or any other kind of analysis, or whether you used, I mean, some kind of benchmarks from these sub competitions. So I was curious why or why not, right? I mean, you did not use these the benchmarks that I presume are publicly available from these sub competitions to compare your tool with existing tools that performed in the previous competition.
The programs are taken from the tool. They are all from real world first, and second, I take the program from the paper, the original paper. Yeah.
I see, but is there any reason why you did not use like the benchmarks from sub competitions that handle the theory?
And do you mean this competition?
Yes. Yes, I presume there is a benchmark on this competition, right? So you did not use the benchmarks from this competition, right? Is there a reason?
Actually, I observed that in this competition, there are many handcrafted benchmarks, and it may come from like planning and AI application. Yeah. Our focus is mainly for software analysis.
Okay, so we have another question from the Slack. So Samantha Saha is asking, did you try to compare with the base Z3 version as you implemented it on top of it, and how much faster it would be? So the question is, did you try to compare with the base Z3 version as you implemented it on top of it, and how much faster it would be? So I guess, I mean, so it's more a question about, I mean, whether you compared it with the base Z3 version.
But I think I have already compared with the basic version of Z3 in the first evaluation. This is unoptimized. This is the speed up over Z3. Yeah.
Okay, so maybe you should take it offline as we are running out of time. So Darko Marinov is just, well, congratulating you for the nice
Okay,
work,
okay.
which is
Thank you.
indeed very nice.
Thank
Okay,
you.
so let's move to the next talk. Next talk will be given by David Trabish. The title is Relocatable Addressing Model for Symbolic Execution. He's from Tel Aviv University, Israel. So it's all yours, David. Please go ahead.
Thank you. Hi, I'm David. I'm a PhD student from Tel Aviv University. I'll present my work about symbolic execution, which is a joint work with Noam Rinetsky. So symbolic execution is a program analysis technique for path exploration, which runs a program with a symbolic input, and it explores only feasible path using an SMT solver. It has many applications, such as test input generation, bug finding, and many more. In this talk, I will focus on two challenges. The first one is path explosion due to the reference of symbolic pointers, and the second one is solving error theory constraints. And we're going to tackle both these challenges using a new relocatable addressing model. So let's start from the first challenge, which comes from symbolic pointers. So symbolic execution tools like CLI, the constraints over memory are encoded using array theory. So every memory object is backed by an SMT array, which maintains the object's contents. And every object also has a concrete base address, and then pointers are resolved to SMT arrays using concrete address values. So a quick reminder about symbolic pointers. So let's have a look at this simple example, which allocates two tables, where each table is basically a pointer to an array of pointers to buffers. And let's see how the memory looks when we execute this program symbolically. So we start with this array of two tables. Then in the first iteration, we allocate the first table. We initialize its pointers with some newly allocated buffers. And then we allocate the second table and also initialize its pointers. And now let's see what happens in this if statement. So here we access the first table with a symbolic offset I. And the accessed pointer expression here is a symbolic value because I is a symbolic value. So these kind of pointers are called symbolic pointers. In this case, this symbolic pointer points only to the red object, which is the first table. And we can encode the accessed value using array theory. So here we can use this select expression over the SMT array that corresponds to T1 and the symbolic offset I. Next, when we access with a symbolic offset J, then we have again a symbolic pointer, but in this case, you can see that it points to two objects which are marked in red. So the question is how we can handle these kind of symbolic pointers. So several approaches have been proposed in the past. We have the forked model, which is used in CLI, which creates a new symbolic state for each possible object. We have the merging approach, which uses disjunctions to avoid forking. And we have the newly proposed segmented memory model, which I will now discuss in more details. So in the segmented model, we partition the memory into segments using static point analysis, such that every pointer is guaranteed to point to its most one segment. And this way we can avoid forks when we access symbolic pointers. So this approach has some limitations. It relies on static point analysis, which can be imprecise for large programs. And as a result, the computed segments might contain many redundant objects. And such segments also correspond to big SMT arrays, which in turn makes the constraints more complex. So let's see how this segmented model works with our example. So we have again the points to relations on the right side that we saw before. And now from the point of view of point analysis, all the objects which are allocated at the red line will be abstracted by the same object. So point analysis can distinguish between the 4 red objects that you see on the right side. So all these red objects will be mapped to the same segment. So now when we go back to our symbolic pointer, then it will indeed point only to one segment, so we can avoid the forks. But you can also see that this segment actually contains objects which are not pointed by our symbolic pointer. So for example, we have here MO5 and MO6, which belong to the second table, while here we access the first table. So what is our goal? It would be nice to somehow create those segments on the fly. The problem is that it's not supported with the current addressing model. To reallocate an object which is already allocated, we need to update all its references into memory. Otherwise, we will have stale pointers. And to do so correctly, we need precise typing information to distinguish between integer and pointer values, and such type information is not always available, especially in programming languages like C. So we propose a relocatable addressing model. And in this model, the base addresses returned by the memory allocator are symbolic values instead of concrete values. We still have a so-called non-overlapping property, which basically says that every object has its unique address range. And we preserve this property using an additional set of constraints, which we call the address constraints. And at last, to keep constraint solving efficient, we substitute those address constraints every time we send a query to the SMT solver. So how the memory looks with our new model. So for example, we have this array of tables where now we see alpha1 and alpha2, both of which are symbolic base addresses, which point to the 2 tables. And then, for example, if you look at the second table, we see alpha5 and alpha6, which point to the buffers that are allocated in the nested for loop. And we have a set of others constraints where each constraint is an equality where the left side is a symbolic base address and the right side is an address value. So now let's see how we can use our new model to implement a dynamically segmented model, where these segments can be actually created on the fly instead of computing them ahead of time. So let's go back again to our symbolic pointer, which points to MO3 and MO4. And now we would like to put these 2 objects in a new segment. So we start with some address constraints. We create a new segment and also add a new address constraint for the new segment. We copy the contents of the 2 objects to the new segment. We deallocate the original 2 objects, and finally we update our address constraints on alpha3 and alpha4. So now both alpha3 and alpha4 are constrained to locations inside the new segment. So now when we resolve again our symbolic pointer, then it indeed points only to our new segment, so we can avoid the forking. But notice in this case, it contains only MO3 and MO4 without MO5 and MO6, as was the case in the original segmented model. Now let's move to the second challenge, which comes from constraint solving. So solving arbitrary constraints is known to be expensive, especially when we have big arrays, which means expressions with many stores. So these kind of expressions of constraints are created when we have an object which is accessed with a symbolic offset. So if during symbolic execution we detect such an access, then we can split this object to smaller adjacent objects. And of course, we can use different splitting strategies. For example, the most simple one is just splitting into smaller objects of equal size. And after this split, if you had a pointer that previously pointed to the original object, so now it may point to any of the new small objects. So potentially, assuming that we use the forked model, then we can actually get here some additional forks. But on the other side, we get smaller objects which come with smaller SMT arrays, which in turn makes life easier for the SMT solver. So how we can implement this approach with our new model? So we again have the same symbolic pointers that we saw before, which points to MO3 and MO4. And suppose now that we follow the path which constrains this pointer to MO3. So now we access MO3 with a symbolic offset J. So we would like to split this object to, let's say, 4 smaller objects. So we first allocate these new objects and also add some additional address constraints for each of the new objects. As it was in the case of merging, we copy the contents from the original object to the relevant locations in the new objects. We deallocate the original object, and finally we update our address constraints. So in this case, we only update the constraint for alpha3. So now it points to the base address of MO7, which is the first new object. And now when we resolve again our symbolic pointer, then you can see that since J is constrained to be less than 100, then this symbolic pointer can point only to the first 2 objects, MO7 and MO8. So we will pay here an additional price in terms of forking, but on the other side, we get smaller objects and smaller SMT arrays. We implemented our approach using CLI, which uses LLVM and STP as an SMT solver. In the evaluation, we evaluated our model in the context of merging and splitting with several benchmarks. So in the evaluation of the merging approach, the main goal is to compare the original segmented model, SMM, with our dynamically segmented model, DSMM. In this table, you can see the sizes of the maximum sizes of the computed segments with each of the approaches. So you can see that with our approach DSMM, we were able to significantly reduce the size of the segments. And this has a direct impact on the sizes of the SMT arrays and also on the performance of the solver. And now regarding the actual performance, so we compared different models. As before, we used SMM and our approach DSMM, and we also considered the forked model, which is used by baseline CLI. And for each program, we checked the termination time and the memory usage. In terms of termination time, our approach DSMM was able to get the best results in M4 Make and SQLite. In APR, the best results were obtained for SMM, the original segmented model. And the forked model, which is baseline CLI, obtained the best results in SQLite. Now, in terms of memory usage, we did not observe significant difference between the 2 segmented models, with a slight advantage for our approach. In M4, for example, the memory usage of the forked model was significantly higher. mainly due to the forking that was caused by referencing symbolic pointers, which is avoided in both SMM and DSMM. Now we get to the evaluation of the splitting approach. So we chose a simple strategy that just splits an object to smaller objects of size n, and we experimented with several values for n. And for each such configuration, we check the speed up with respect to Bayes-Stanley, which uses the forking model. So the overall result that in most of configurations, we were able to get a nice speed up. So throughout the evaluation, we observed two main patterns. For example, in SQLite, we observed that with smaller values for n, we got more speed up. On the other hand, for in make, when we used the smallest value for n, the performance was worse than when we increased the value of n till some point. We got more speed up, but when we first increased the value of n, then the performance actually got worse. In general, what we have in this experiment is a trade-off between number of explored paths and the complexity of constraints. So a small value of n means that we potentially have more explored path and more simple constraints. For larger values of n, we have less path, but the constraints are more complex.
If you have 1 minute.
A few words about future work. So in the evaluation, we evaluated separately the merging and splitting approach, but we can also combine them in the same run. We can predict better when a merging or splitting is likely to be beneficial and design more sophisticated splitting strategies. You can visit our project page, and our code is also available on GitHub. That's all. I'll be glad to answer questions.
Okay, thank you very much for the nice talk, David. So far we still don't have questions on Slack. I mean, still waiting, right? But I do have questions. So can you move to the last slide? Yeah. So for future work. I mean, so my first question was about combining, merging, and splitting. I was a bit confused why you evaluated your approach. I mean, separately. I mean, merging and then computing. I mean, costs for splitting separately. So I thought, I mean, these would run simultaneously, right? I mean, during symbolic execution, these operations would occur, I mean, at the same time. So I was a bit confused what was the evaluation set up for your experiment. So can you elaborate on this?
Yeah. So the two applications that we have for this model. So each of them is solving a bit different problems. So the first one is trying to address the problem of symbolic pointers that point to many objects. And second one is a general, you can see it as an optimization for solving arbitrary constraints. So regarding the combining of these two merging and splitting transformations, so you need to be, it should be supported with this model, but you need to be a bit careful because they do the opposite. For example, if you, let's say you start with Bayes-Stanley and you have a symbolic pointer that points to, let's say, 5 objects, and then you merge them to one segment, then probably you don't want to split them back to smaller objects. So it should be possible to do that, but you need to do here some additional work in order to avoid some this kind of weird situations.
And does your strategy would enable merging them back, I mean, to a single, well, I mean, a cluster? I mean, after you split, I mean, you start from some, I mean, some merge block and then split, and then would you be able to merge them back?
So I think it should be implementable, but you need to be a bit careful of how you might do some need to do some modifications to how your path constraints look. But I think that it should be possible.
All right. So a quick question from Slack. I mean, Xuan Xie is asking, nice work. Did you measure coverage? I mean, he's asking.
Yeah. So in the benchmarks that we used are inspired from the original papers that introduced the segmented model, and there we take benchmarks which terminate, which means that CLI explores all the paths. So in this case, the coverage is basically in all cases where the analysis terminates, so you get the same coverage. So so it's kind of not so relevant in this setup.
Mm-hmm. But in any way, because of this property, I mean, did you use coverage, I mean, as a correctness criteria, just to make sure that everything was okay? I mean, just out of curiosity.
Yeah, we did mention it in the paper, but internally, yes, we did it in the splitting approach and in the merging. Yes.
Okay, a very last question from Nazareno Guerre. Very nice presentation. How you specify is the technique to CLI-like tools? I guess if the technique is for CLI-like tools, would a version of the technique be mapped to tools like SPF, the Symbolic Pathfinder Java?
Yes.
Yeah.
So
quick answer, because I mean we are running out of time.
Yeah. So I think the merging approach is sort of general. So here we presented it when we used error theory, but I think it can be used even if you use different logic to encode symbolic accesses. So I think it should be able to implement it for other tools as well. The splitting approach is more specific for array constraints, which are not used in other tools, or at least not in all other tools.
Okay, David. So thank you very much. Very nice talk. Okay, let's congratulate.
Thank you.
All right. So let's call our next speaker, Frank Boos. So I think the GD, student volunteer, is going to play a video. I mean, that's what Frank asked us to do. So his paper is running symbolic execution forever. So this paper won like 3 badges for artifact, functional, available, and reusable.
Today I'm going to present
all right. Okay,
our new paper, Running Symbolic Execution Forever. This is joint work with Martin Nowak and Christian Kadar. The paper itself is about our new memoization extension for the CLI symbolic execution engine. But before I dive into the details, let me introduce symbolic execution so that we are all on the same page. In a normal execution, an application processes data from various sources, such as files, network packets, or user input. However, all these different input values determine just a single specific path through the program that typically resides in an output shown on the screen or written to a file. Symbolic execution, on the other hand, replaces inputs or parts thereof with symbolic values. Such symbolic values represent the whole domain of an input and not just a single concrete value. Hence, a symbolic execution can follow all feasible paths, resulting in an execution tree. We will come back to the tree a little bit later. Whenever a symbolic execution engine finishes a path, it can produce a test case or a crashing input if a bug was found. Symbolic execution faces 2 major challenges. The first one is a constraint solving overhead. For every new branch, a symbolic execution engine has to check its feasibility. On critical instructions, such as divisions, assertions, or memory accesses, it performs safety checks, and when a pass terminates, it generates concrete test cases. All of this is done with the help of an SMT solver. The second challenge, as you can imagine, is path explosion. Each if or switch statement or loop with symbolic condition potentially creates new branches that have to be explored by the engine. In practice, symbolic execution engines terminate paths when they run out of memory. To quantify these terminations, we conducted a small experiment. We ran 87 core utils for 2 hours max with clear symbolic execution engine and its default memory limit of 2 GB. Don't worry, we also ran with 10 GB with almost the same results. In this experiment, we counted all the paths that were early terminated due to memory pressure. The result is shown in the graph. Every dot is a different application and the y-axis shows the amount of paths that got early terminated. You can see that for most applications more than 60% or even 80% of paths were interrupted. And currently there's no mechanism to recover and continue such paths. Let's go back to our exploration tree. We have a very large amount of early terminated paths. We also have a large amount of normally terminated paths. And we were wondering, how do we enable a symbolic execution engine to explore the early terminated paths? Remember, behind every interrupted path is a potentially huge subtree loss for exploration. We had 2 goals. First, when we explore a path to the point of interruption to make further progress, we don't want to resolve all the solver queries. And second, we don't want to re-execute the already explored subtrees. The solution to the first problem is Algorithms 101. Use memoization to store and reuse results of expensive computations. In our case, we store constraint solving results in the execution tree nodes and persist the whole tree to disk. A data structure reflecting the execution tree exists in most symbolic execution engines in one way or another. Let me show you an example. Let's assume that we have already recorded a symbolic execution run and the tree with all our results is stored on disk. In a subsequent run, we start with the initial state shown as green circle. Before the execution starts, we read its metadata from disk and attach it to the node. The metadata contains all solver results up to the next branch. So we continue the exploration and reuse the solver results. When the execution branches, we read the metadata for the child nodes from the database and free the metadata for the parent node. That way we ensure that our approach has a very low memory overhead in comparison to normal symbolic execution. Now let's assume the write path in our current execution tree progresses beyond its memoized data. At that point, the path switches to recording mode and stores all new results from the SMT solver in its metadata. On the next branch, the metadata for that node in the database is updated and freed from the current tree as before. When the new child nodes terminate a branch, they are eventually written to the database. As mentioned previously, we not only want to reuse constraint solving results, we also want to prevent a subsequent execution from re-executing previously completed paths. Therefore, we also store termination information in the node metadata. So let's assume the leftmost recorded subtree was completely explored in previous runs. Now, when that path branches in the current execution, we read the metadata and immediately detect that we hit a completed subtree. The path is then terminated and removed from memory. No further information is read from database and no additional instruction is executed. At that point, some of you might think, wasn't there a paper already about memoization and symbolic execution? And you're right. Guwei Yang, Corina Pacheco, and Safras Khurshid published a nice paper about it at this very same venue 8 years ago. The implementation at that time was based on the symbolic extension of Java Pathfinder. However, we think that our approach and evaluation is different enough and provides new insight worth publishing. For instance, their implementation requires that re-execution runs use the same exploration strategy as the recording run. We think it's important to use different search heuristics for quick first exploration, to find bugs or to generate high coverage test cases. Also for path pruning. The whole tree needs to be brought back to memory, and interesting paths for further exploration must be marked explicitly. Our approach, however, is completely dynamic and just relies on the chosen exploration strategy during re-execution. Additionally, from the paper it's actually not clear if that approach scales. The execution times for the benchmarks were very short in the range of seconds or a few minutes. For us, memoization lays the foundation to explore new code in large applications, and that requires much longer runtimes in the range of at least several days. And last but not least, they have no means for divergence detection. But what exactly are divergences? Divergences occur when a re-executed path takes a different branch and hence executes a different sequence of instructions as its recorded counterpart. Let's again assume we have a recorded execution tree on disk and want to explore the unfinished path with the arrow. In the current execution tree, the execution is at the second to last node but then takes a different branch in the program. For instance, it iterates a loop one more time before exiting it. At that point, the symbolic execution engine would reuse recorded solver results in the wrong locations, meaning that infeasible paths become feasible, or bugs are missed or reported as false positives. The causes for divergences are manifold. It can be changes in the environment, such as the number of files in a directory or the free space on disk, or in some execution engines, the shared address space among execution states. Here, the exploration strategy influences the order of allocations. That means addresses returned by the underlying allocator vary between runs, and applications that use, for instance, hash maps over pointers diverge. Actually, a large part of our engineering effort went into the execution engine itself to make it more deterministic. To detect divergences, we associate the hash sum with every basic block before execution and store cumulative checksum in the metadata of each node during execution. Assume we reach a node with a checksum of C0. When a state progresses, it traverses a sequence of basic blocks. The hash of each reached basic block gets combined with the current checksum and is finally stored in the child node during the next branch. During re-execution, the computed checksums are compared with the stored values, and paths that diverge are reset. We have implemented our approach on top of CLI 1.4. We named our extension MoCLI and evaluated it extensively on 93 benchmarks. Among these are redev, diff, find, grep, libspng, tcpdump, and 87 core utils. We removed some core utils from the benchmark set, such as kill or change mode, for they sometimes interfere with our test setup. We are aware that the symbolic execution community tries to move away from core utils as benchmarks. However, in this project, core utils were particularly useful. Some of its applications are instruction-bound and create huge and challenging execution trees. Others interact heavily with the environment and helped us to develop an effective divergence detection and also to find non-deterministic behavior in CLI. More complex tools are actually less challenging for memoization, as the trees are much smaller and the slow solver queries would hide inefficiencies in the implementation. For the first experiment, we recorded 87 core utils with a default search heuristic, a combination of random paths and a coverage-guided search, shown as randomcuff. We set a time limit of 2 hours and afterwards re-execute the same execution with and without path pruning and with two different search heuristics, randomcuff and diff first search. We do not progress beyond the recorded execution and only measure the effectiveness of memoization in that experiment. As you can see, when we replay the execution with the same strategy, the median execution time decreases to 13.5 minutes. And with enabled path pruning even to 8.2 minutes. Using the more lightweight DFS strategy reduces the median execution times further to 6.4 and 5.4 minutes respectively. We also measured the time spent in the different subsystems of MoCLI and, as one would expect, the time spent constraint solving is reduced significantly. Still, there is a small fraction of queries we do not memorize. Those are queries that contain addresses and would lead to divergences otherwise. Also visible as the missing blue section is a smaller amount of time spent in the searcher for the more efficient DFS strategy, as mentioned before. You might notice that we only report the results for 37 out of 87 core utils here. The reason is that we remove all tools that terminate states due to memory pressure or diverge in at least one of the runs. Be aware that Memoization works perfectly fine with those applications, we just have to make sure that we compare the exact same executions here. How large are the execution trees and how much disk space is needed to store them persistently? To answer this question, we report the file sizes of 66 executions of applications that reach the 2-hour time limit. As shown in the graph, the tree sizes vary between roughly 2,000 and 21 million nodes. On disk, the tree sizes range between 3.1 MB and 1.5 GB. Evidently, disk size and the number of nodes correlate with an average size of 85 bytes per node. We also evaluated the occurrence of divergences. For that, we recorded 2-hour executions of all core utils with random cuff and DFS search heuristics, and re-executed the same executions without path pruning, but also with the 2 search heuristics. From this experiment, we excluded again the tools that terminate states early due to memory pressure, or obviously do not diverge. The number of the remaining tools per experiment is shown in the parentheses. The graph clearly shows that a sparse and shallow tree as a random cuff is less affected by divergences, as smaller subtrees are reset and hence less instructions are lost. Lost here means that we cannot reuse the recorded results as we remove the affected subtrees from the database. But this is the result we expected. More surprising is that the change in the search heuristic during re-execution doesn't cause larger differences in lost instructions. Remember the first experiment where I showed you how many paths are terminated due to memory pressure. In that experiment, we observed 14 applications that terminated so many states early that the execution engine was able to successfully explore the remaining paths to completion, and then ran out of states before the 2-hour time limit. That means, no matter how much time we have at our disposal here, we cannot make any further progress. One goal of our approach is to enable the execution engine to explore the interrupted paths. In our final experiment, we memorize the runs of those 14 tools and then restart with memoization and path pruning. We do not set a time limit, we just restart the execution whenever the engine runs out of states and terminates. We stop the experiment when the overall execution time for a single application exceeded 7 days. Each dot in the graph represents a single run. We had to restart the applications between 20 and 105 times, with 2 exceptions. Dynamically and some terminated regularly with the first re-execution, meaning that we fully explored the execution tree. Format was the only tool where we encountered single runs lasting several days. In fact, we had to exclude the last data point for the sake of readability of the graph. It is located close to the 10-day marker. On the left side, you can see the number of instructions that were re-executed to reach the end of a memoized path. On the right, we report the number of new instructions per run. The number of new instructions is typically 1 to 2 magnitudes of order higher, meaning that our approach is effective and the exploration progresses. For 6 of the 14 applications, the longer runtime led to new coverage. The relative increase ranges between 0.78% for cut and remarkable 17.56% for tuck. Interestingly, the increase in coverage for tuck happened mostly on the last day of our experiment. Keep in mind that we do not make use of special or even different search heuristics here. The progress and increase in coverage is only due to our memoization framework, showing that it indeed enables us to explore previously inaccessible subtrees. In this talk, I've presented our new memoization extension for CLI called Memoization. Memoization enables you to efficiently store and reuse solver results as well as prune previously explored subtrees. Furthermore, it is able to provide a global view of all consecutive executions that can be used to analyze symbolic execution experiments and to develop new search heuristics. The artifact with Mowgli, the benchmark applications and the complete set of experiment results is available under the given address. We plan to upstream most of our changes. Let me finish with some shameless advertising. After the very successful first CLI workshop 2 years ago, we are organizing another one next April. So if you're working on a project that is based on CLI or symbolic execution in general, or if you're using CLI as a tool in your company, please consider submitting a short talk. Thank you.
All right, so thank you, Frank Boots. Thank you very much, for the nice talk. And we still, have no questions on Slack, but hopefully, we're gonna have some in some time soon, right? So I have some questions for you. Actually, we already have one, but well, did you try to use a green? I guess you know. This work of Willem Visser and people from South Africa on sharing, constraints and reusing them across different projects and so on. So did you try to build on those ideas and canonicalizing, these constraints as opposed to save, these decision trees for path constraints?
The thing is with those caches or those persistent caches is you have a large overhead. So you're storing all the expressions, whereas we only store for a feasibility check a single bit. So it's much cheaper for us to just store a single bit. And the other thing is with those caches is that you need somehow an eviction strategy. You just keep storing and storing and storing, and you never know if you need those results ever again, right? And this might also be expensive. And what we also, the third reason is what we also encountered is that in our first version, we put our replay mechanism behind our caches in CLI. So we thought that when we pre-populate all those caches, we might actually be even faster. But the thing is that our caches are so fast that you basically need an approach or a persistent caching mechanism that can preload results, or is really, really fast, and that doesn't work in our case with CLI. It's just too slow to load and from disk a result for a cache. So the other option is you would read basically the whole cache into memory, and not just for every query you query it. That might work, but then again, you end up after some days with a huge cache, and you never know what you would reuse in that case.
Okay, so let me move to another question from David Trabish. His question is: did you encounter cases where switching such heuristics was needed to achieve better results? For example, more coverage.
We haven't evaluated yet. So basically that lays the foundations to do exactly that, to play around with different search heuristics and make sure that we don't re-execute the same trees and paths during different re-executions. So that's basically it's just the foundations here. And now we do the other part.
All right. Any other questions from the audience? Okay, just to make sure, Frank. Did you actually save in memory? On your cache, like the execution tree. The data structure that you actually use is like a tree.
Yeah.
For the execution tree of your program. All right.
So the execution tree already exists in CLI. So we just add some metadata to the nodes. But we only keep those metadata in active nodes, basically in the leaf nodes, and all the other ones is freed and written to disk and loaded from disk. And so that we have a very low memory overhead during runtime with that approach. That's a nice thing here. And for the solver results, we just store a few bits or constant, never the whole query or the expression. So it's very, a very lightweight approach.
Okay. Okay, nice. Okay, so let's congratulate our speaker again. All right, claps for you, and thank you. And now we are gonna have a break until the next session. So thank you, everybody. That's it.